Okay, and we are ready to go. All right, so today, last time we were just playing around with limits and I lost track of time. My watch died. I'm not used to looking at the clock up there. I must have glancing at my wrist. Anyway, let's continue talking about limits. Let's get a little bit more formal. We're not going to get super formal because we don't need to in 205. 1.6. No, 2.2. Let's continue. So now let's talk about the definition. How do I want to say it? Let f of x be a function we say the limit of f as x approaches a is L, and write, so now here I'm going to introduce the notation. It's LIM, all lowercase, you write x, little arrow approaches a of f of x. Right? So this is the limit as x approaches a of f of x equals L. Right? So we say that and we write this if as x gets close to a, your f of x gets close to L. So that's the definition of a limit. It's not the precise definition. I mean, if you guys were math majors, the definition would look a lot crazier with a lot of Greek letters all over the place, because mathematicians don't like vagueness. So me saying close, what does that mean? Like so a foot away, an inch away, a centimeter away? Like what's close, right? At this point, we don't really need to know that. We're going to look at it in a very intuitive and computational sense, so we won't need to know that. But basically, we're looking at, so one thing I want you to note, the following. F of x need not be defined at x equals a. Right? Whether the function exists there or not, we don't care because we're not going there. We're just getting very close to there. I want you to that's why I underlined the word close, because that's something I really want to emphasize. We don't really care about being at the point. We care about inching towards it, getting super close to the point. So your f doesn't actually have to be there. In fact, if your f is defined there, that will give you some other properties that we'll talk about later. Right? So basically, the limit is tracking the y value as the x value gets close to some number. So you can sort of think of it as the limit is the y value you get close to as x gets close to something. Right, so when you're talking about limits, you're really watching the y value. You're inching the x value somewhere, and then you're watching what happens to the y value. Right? That's really what you're looking at. So you're watching the y value. You're watching how the outputs of the function behave as your inputs approach a certain number. Your function does not need to be defined at that point. It could be a whole, it could be an asymptote, it could be whatever. But sometimes it might be important for us to know what happens close to that point, right? And we were playing around with some pictures last time and to kind of give you a conceptual understanding of what that means. But this is kind of how you want to think about it. As I said, it can get more detailed, but for 205 we won't need any more details in this. And this is the notation, right? So you'll write this. So I can do an example here. Example, we can write the limit as x approaches 1 of x plus 1 is equal to 2. This means if x gets close to 1, y equals x plus 1 will get close to 2, right? So as my x value inches closer to 1, my y value, the output of this function, is going to get super close to 2. Right? So the last, I believe it was the last example last time. Another example, if I took the limit as x approaches, was it minus 2, I think? X squared minus 4 over x plus 2. We did that last time when we analyzed the graph, and now we can actually write that the answer here was minus 2. Right? Was that minus 2? You wrote that as x plus 2 times x minus 2, and then we plugged in minus 2, so this is minus 4, right?
Yeah.
So notice, at minus 2, our function doesn't even exist, but we don't care about that. We just care about getting close to it, and we're watching those values. And if you had a calculator, and you started plugging in values closer and closer to minus 2, like minus 1.999, then minus 1.99999, then minus 1.99999, you'll notice that the outputs are getting closer to 4. It'll go like minus 3.9, minus 3.999, minus 3. And you're like, oh, I see what's going on. So we're not actually there. We just want to see what happens when we get close to there, right? And that's actually pretty important. You'll see why in the next section, and even later on when we're doing curve sketching, why knowing what happens close to some point is going to be important. It's what calculus is about, actually. Yeah, so that's the idea of a limit. We're just watching the y values for what happens when we manipulate our x values towards some point. Another thing to note, it's important to have a definite answer. Right. So we want to know what is the y value approaching. It's going to be, you can't have more than one answer. There should be one answer, and otherwise the limit does not exist. Otherwise, the limit, the technical term you'd say, does not exist. Or you can just write d and e, and I'll know that's what you mean. So it's possible for the limit to not exist. So for example, limit as x approaches 0 of 1 over x does not exist. Right? And the idea was, we looked at this last time, we're approaching 0, but there are actually two ways you can do it. One way is to come from the right, and it turns out we're going to positive infinity. The other one was to come from the left. Turns out we're going to negative infinity. These answers cannot agree. I can't say you're getting close to positive infinity and you're getting close to negative infinity. That doesn't make sense. So just say the answer does not exist. There is no single value that you get close to. So it's possible for limits to not exist. But it's not the same as being defined at the point, right? You don't actually care about being at the point, just getting really close to it. Did I mention that? Yes, mention that. There are laws, of course there are laws, rules, governing limits. Here I'm really talking about algebraic laws. One, it turns out for limits you can actually factor constants out. So, let me say, suppose the limit as x approaches a of a function, and the limit as x approaches a of some other function exists. Right? Meaning, I can take the limit of these functions as you approach a and I can get an answer. Right? And c is a constant. Then, 1, it turns out if you take the limit of a constant times the function, this is just going to be equal to a constant times the limit of the function. You can factor constants out. 2. Limits distribute across sums, right? So if I'm taking the limit of f of x plus g of x, plus or minus, I would get the limit of f of x plus or minus the limit of g of x. Limits also actually distribute across products, right? Which is not a typical thing. So if I have f of x times g of x, then if I take the limit of a product of functions, and each one individually exists, and I should probably say exists and are finite. For emphasis. This is actually equal to the limit of the f times the limit of the g. So knowing these rules allows us to take limits of more complicated functions, given the fact that we know how to take limits of the simpler functions that make them up. Or limits distribute across divisions as well. So if I have f of x over g of x, this is equal to the limit of the f of x divided by the limit of the g of x. If the limit of g of x is non-zero, of course, because you cannot divide by 0. If I take a function and I raise to a power, then the limit of that is just, I look at the limit of the function itself, and I can raise that to the power. N is a positive number. I could make it negative if I want this. I want to be able to take reciprocals. I just have to make sure this is non-zero, but in your book they just say positive. It'll work in general. Wait for you guys to copy that now. So those are some rules of how limits can work with algebraic operations, adding, subtracting, multiplying, dividing. There's also the notion of a one-sided limit. Let's talk about those. As the name suggests, these are limits taken from one side. Right? Because if you're on the x-axis, right, for some random x value, how many ways can you approach it? They're actually from two ways. You can come from the right, you can come from the left, right? We're talking about functions like that, where they didn't match up earlier. Notation. You write this, x approaches a, and you write a little plus sign of f. This is the limit as x approaches a from the right. Right? You're a plus a little bit, so you're coming from the right. Right? So here it's like, this is your x-axis, here's your a. This is only caring about the limit as you come from this side. Right? Tell me what the y value is doing when I come from this side. I can write a with a little minus as the power. And that's the limit as I approach from the left. Right, so here's my x-axis. Here's that a, but now I only care about this side. Okay. Now with that notion, we can actually get answers when we otherwise wouldn't have. So with this notion, we can say the limit as x approaches 0 from the right of 1 over x versus the limit as x approaches 0 from the left of 1 over x. Here we can actually define answers. Right? So remember, my 1 over x looks like this. So if I'm getting close to 0 from the right side, what's happening to my function? It's shooting up, right? I call this positive infinity whenever my function does that. Right? If I'm coming from the left side, though, it's shooting down. So I can say it's negative infinity when that's going on. Right? So this notation here just means I'm talking about limits getting close to something, but only from one side at a time. That's the notion of a one-sided limit. Limit as x approaches a of f of x exists precisely when both one-sided limits exist and have the same value. i.e., which means that the limit, the overall limit, this guy, exists and equals this common value. i.e., if the limit as x approaches a from the right of f of x is the same as the limit as x approaches a from the left of f of x, and they're both equal to L, then it means that the overall limit as x approaches a of f of x equals L. Right? When you're coming from the right and the left, you must match up. Your y values must give you the same, so you can say, oh, that's the y value we're approaching. Right? If that doesn't happen, your limit does not exist. It does not exist otherwise. So let's talk about a similar example to this one. Let's look at a similar function. Again, I'm looking at one side as I approach 0 from the left and the right, but now I'm making it slightly different. 1 over x squared. 1 over x squared. What does 1 over x squared look like? Almost looks like this. Right? Now, as I'm approaching 0 from the right side, what's this function doing?
Shooting up to infinity.
Shooting up to infinity. And as I'm approaching from the left side, what's it doing?
Shooting up to infinity.
Shooting up to infinity. This means, overall, the limit as x approaches 0 of 1 over x squared equals infinity. So I can see an answer here. Whether you're coming from the right or the left, we're still blowing up without bound. Right? For 1 over x, this didn't work because the right side went in one direction, the other side went in the opposite direction. So there's a notion of one-sided limits. You come from the right or the left. These must agree for you to be able to say the overall limit has an answer. Right? And you define it to be that common answer, whatever it is. Yeah. So plus means coming from the right, minus means coming from the left. Let's do an example of computing some of these. Should we talk about continuity first? Let's do some examples. There are a couple cases. The first one is the least interesting one. If f of x is defined at a So if our function is defined at the point we're approaching, then the limit as x approaches a of f of x is going to be f of a. Right? Just plug in the number. So for example, the limit as x approaches 1, 2x plus 1, limit as x approaches 2, 2 minus x squared. So if I ask you, what is the limit of this function as x approaches 1? Right? So you agree this, the limit as x approaches 1 of 2x plus 1. In other words, I'm asking, what is the y value approaching when my x gets close to 1? Right? Now you'll notice here, this is a polynomial. Polynomials are defined everywhere. They're nice, right? So I know it works at 1. So all I just do is just plug in that 1, right? Forget about getting close. I can actually be there. So I just plug in a 1. So the answer here would be 3. Similarly here, this is another polynomial, right? So it's defined everywhere. In particular, it's defined at 2. So if I want to find what is the y value getting closer when x gets close to 2, I can just plug in 2. So now I know it's minus 4. Right? I don't have to go through the trouble of drawing the graph because it's defined there. I just plug in the number. By the way, note what happens here. I'm actually applying a rule in the background. When I look at limit as x approaches 2 of 2 minus x squared, technically what's going on is this is a sum. I'm applying the limit of each term. can think of it that way. So if there's a plus or minus separating things, you don't worry about it. You just deal with each of them separate, right? What's the limit, what's the y value getting close to when x gets close to 2? Well, if your y value is always 2, then it gets close to 2, right? In this case, I can just plug that 2 into x. In this case, I can plug that 2 into that guy, right? Usually skip writing this step though, but it actually happens in the background. Right? But you have that notion of, if there are plus or minuses separating things, I can just take the limit of each individual exponent. Or if you notice the function as a whole is just, its technical term is continuous there or defined there, you just plug in that number. Any questions on that? Yeah.
What if you had something like the limit as x approaches it to a 3?
It would be 3. Right? Let's look at that constant. Why is, I can write that down. If your x's aren't there, then the limit is just going to be whatever the thing is. Right? So for example, the limit as x approaches a of c, which is a constant, is always going to just be c. Right? The reason is, well, if you have f of x equals c, that's just a horizontal line going through C. So whatever number I'm at, what is my y value getting close to when I get close to this? C. What about if I'm getting close to here? C. Getting close to here? C. The output is always at C, right? So your limit of a constant is just itself, right? That's what your y value is always there. That's what it's always approaching. So yeah, otherwise, if you can plug in that x value, just plug in the x value. Another thing to note, if a part of a function is not defined, the limit may not exist. I'm going to talk about where functions are defined and how we can talk about the limits. Example, limit as x approaches 0 of 2 plus x plus 1 over x. Right, now let's say I gave you that. Right? So like, oh yeah, 2 is fine, I can plug in 0 to x, no problem, but this guy is not fine, right? In fact, what is that? Well, this guy would go to 2, this guy would go to 0, but what was the limit as x approaches 0 of 1 over x?
That doesn't exist.
Does not exist, because the right side and the left sides didn't match up. So you know, overall, does not exist, right? So yeah, this part of your function behaves, but that part of your function goes crazy and messes up what your y value would approach if it approached anything at all, right? So be careful with the sum. So this is sort of what I'm saying. Sometimes you have to dissect things. Right? So these are the nice kinds of limits. When your function works at the point, you can literally just plug in the point. It's not going to be a big deal, right? That's not the interesting case. Case 2. What if f of x is not defined? At x equals a. Then you have two options. There are kind of more, but it's really one of these two usually is going to give you the answer. One is to simplify to get rid of the part that messes up. Two analyze the function numerically. That means plugging numbers closer and closer to a and watch what the y value is actually doing. Usually you'll be in a calculator, so we're not going to do this a lot. Plug in numbers closer and closer to a and watch the y values. See if your y value appears to be getting closer and closer to some other number. Do an example. Well, let's analyze an example that we've seen before. Minus 2 of x squared minus 4 over x plus 2. Now here's an example. If I'm taking a limit of something where the function is not defined at the point, because if I plug in minus 2, I divide by 0. So what we do is we see what the problem is. It's the denominator, right? So what I'm going to do is I'm going to try to simplify to get rid of the part that messes up. Can I simplify this to get rid of the denominator?
Yeah.
Yeah, so this is just going to be equals the limit of that guy I can factor. Then I realize I can cancel this 2. And so now this is the same as the limit as x approaches minus 2 of x minus 2. Right? Because I don't actually care about being at negative 2. So I can cut away parts of the functions that makes that a problem. And so getting close to minus 2 of this function is pretty much the same as getting close to minus 2 of that function, right? Because I'll never actually get there. I just care about being close to there. And so now, at this point, puts me back in the first case where my function is nice. I can just plug in the answer. And so that would be equal to minus 2 equals minus 4. Yeah, did you have a question?
Yeah, last class I'd actually asked you about this exact thing, to which you said that you can't just plug in negative 2 into that because
I can't plug it into here.
Yeah,
Right.
I know that, but you just said if you can't plug in that negative 2 into that function, and you're saying that x minus 2 is the same exact thing as that first function, then...
Oh, that's not what I'm saying.
I don't get it.
I'm saying that the limit of this is the same as the limit of that. It's not me saying the functions are the same. Because in fact, we did this last time. Basically what this is saying is, as I approach negative 2, they behave the same way. It doesn't mean they're the same function. If I were to graph y equals x minus 2, the graph looks like that.
Yeah.
If I'm to graph x squared minus 4 over x plus 2, the graph looks like that. They're actually two different functions. It has two different rules.
So the x squared minus 4 over x plus 2 is not defined at negative 2.
It's not defined, but this is defined everywhere.
Including
at negative 2. So they're not the same function.
Mm-hmm.
However, this one has a problem at negative 2 when that one doesn't. But the thing is, when I'm a limit, I don't care about being at negative 2. I just care about getting close to it. So it turns out that this one, when I get close to negative 2, it behaves pretty much the same as this one when I get close to negative 2. The y values will be similar. It doesn't mean they're the same function.
That means if they have the same limit, that means I can say that the limit of x, the limit as x approaches negative 2 of x minus 2 is negative 4. But that means I can also say the limit as x approaches negative 2 of x squared minus 4 over x plus 2 is also negative 4.
Yes. When you're talking about limits, you're talking about the behavior of the y value when your x value does something. So you're not saying the functions are the same, but they can have the same limit. There are tons of functions that will have limit minus 4. I can say, the limit as x approaches minus 2 of the function minus 4 is also equal to minus 4, right? It's not the same function, right? But this graph goes through minus 4. It's always minus 4. Of course, if I approach negative 2, I will also approach minus 4, right? So the fact that the limits are the same doesn't mean the functions are the same. This function has a problem, that one doesn't. So the idea is, because I don't care about actually being located at the problem point, I can simplify it to get a function that behaves very similar, to which I can take a limit.
So by extension, if like that other complicated thing of f of a plus h minus f of a over h, like you're just plugging in that same exact formula of like f of a plus h, and then you just simplify it such that you cancel out the h's on the top and the bottom, and you just simplify that function. But other than that, it acts the same way.
Yeah, exactly. Which is kind of why I was telling you guys earlier, oh, when we solve the difference quotient, we kind of want to kill the denominator. This is kind of what, right? This is what I was trying to get to, right? Because we want to get to, we want to make our function nicer so that we can find a limit for it, right? Because as it was originally, we can't do anything. But when I simplify it to kill a problem spot, now I can get an answer. Right? The big deal is I don't care about being at the problem spot. And that's what the limit gives me a power to do, to inch close to something where I might have a problem otherwise. What else did I want to tell you? I told about one-sided limits. Where can I erase? That was last over there. Let's talk about continuity. So leave it to mathematicians to get the romance, take the romance out of everything. Basically, a function is continuous if you want to think of it in a frilly way. It means you can draw the graph without lifting your pencil off the page. Not good enough for a mathematician. What does it mean to be able to draw a graph without lifting your pencil off the page, right? That's what we're going to try to define right now. Let's actually write down the definition. We say that f of x is continuous at x equals a if the limit as you approach a of our function f of x is actually equal to the value of the function at that point. And this is again a good example, but let's see if I can note. Three things need to happen here. One, f of a must be defined. There must be an output when your x value is a, otherwise it's not going to work. Otherwise the right side of the equation won't make sense. Two, the one-sided limits must exist as I approach a from the left of f of x, and as I approach limits from the right of f of x, they must exist. And three, they must equal. So the limit as I approach from the left must be the same as the limit as I approach from the right, and they both must be the same as the value of the function. So basically 2 must be equal to 3. Must be equal to 1. 1 must be equal to 3. Step 1 must give me the same value as step 2. Right? Now when these three conditions are fulfilled, what it means is I can draw the graph without lifting my pencil off the page. So if you look at this guy, what happened here? Let's say I'm approaching negative 2. Negative 2. And I ask you the question, is this function continuous at negative 2? And the answer is yes. I can draw my graph without lifting the pencil off the page. How do I know I can do that? Well, if I take the limit as x approaches negative 2 from the left side of this function, I would get minus 4. If I take the limit as x approaches negative 2 from the right side of this function, I would get minus 4. And if I look at the function itself at minus 2, it gives me minus 4. All these things line up. Here though, is this function continuous at negative 2? The answer is no. I would have to lift my pencil off the page and start again. Why did that happen? Well, if I look at the limit as x approaches minus 2 from the left of this function, the answer is actually minus 4. If I take the limit as x approaches 2 from the right of this function, the answer is again minus 4. But then if I ask you, what is f of minus 2? That does not exist. Right? So my limits worked out, but my function messed up. Right? There are cases when the other one is different. Like so, example, let's say my f of x equals, let me do a picture first of a graph, and then I can give you a formula that illustrates the same kind of example. Let's say I'm approaching 1, and here, the function did that, and the function did that. This is at minus 1, this is at plus 1. Right? Now you can clearly see from the picture, I can't draw this without lifting my pencil off the page. But how did the math tell me that? Well, if I ask you here, what is the limit as x approaches 1 from the right of f of x?
1.
It's 1. As I'm coming on from the right, getting close to 1, my y value will get close to 1. Or if I see the limit as x approaches 1 from the left of f of x. Well, if I'm approaching 1 from the left, I'm on this side of the curve. What's the answer? It's getting close to minus 1. It doesn't matter that I'm not defined there. That's not what I care about. Getting close to it is what I care about. So this means that my limit as x approaches 1 of f of x does not exist. By the way, so what is f of 1 actually?
1.
It's actually 1, right? Because it's filled in here, not here. So my function works, the thing is my limit's messed up, which means I cannot draw this without lifting my pencil off the page.
Didn't you just say you can have 2 outputs though earlier?
Huh?
You said you can have 2 outputs.
What can I have to
F1 is, how is F1 1?
This is a gap.
Oh,
This is filled in. It's a hole. So I can actually be here. So a lot of things can go wrong. So there's another instance where I need to lift my pencil off the page to be able to draw a graph. So in the first case with this x squared minus 4 over x plus 2, the limit existed, but the function wasn't defined. Here, the function is defined, but the limit doesn't exist. It turns out you can have both of these things working, and you still not continue. Let's look at this function. Go through 2. Let's say this is 3. Let's say that's 5. So now this is my function of x. Now if I ask you, what is the limit as x approaches 2 from the left of f of x? What is the limit as x approaches 2 from the right of f of x? What is actually f of 2? What's the limit as you approach from the left?
3.
3. Limit as I approach from the right? Still 3. So the limit actually exists. Is my function defined at 2? Yes. What's the value? 5. Right? So now the third condition wasn't fulfilled. So step 1, does the limit exist? Yeah. Step 2, is the function defined? Yeah. Are they the same? No. Basically what that means is, when I'm drawing this, I have to lift my pencil, fill that in, come back here. Right? So there are a lot of cases where a function can mess up. And not be continuous is what it's called. Continuous just means I can draw it without lifting my pencil off the page. Let's look at another example. What term is it? Let's look at another example. Let's make it a piecewise function, even though we've been doing this already. In fact, let's be a little trickier. So let f of x equals absolute value of x divided by x. Oh, after I make one remark, which I should have made earlier. So note we have a definition for being continuous at x equals 8. Right? So notice that the first definition I talked about being continuous at a point. We say f of x is continuous. Just continuous, not continuous at a point, continuous in general, if it is continuous at each point in its domain. So if this thing works out for every single point along your function, then we know it's continuous in general. Okay, let's look at this example. Absolute value of x over x. Tell me how to deal with that. So the question I want to ask is this continuous? Can I draw that graph without lifting my pencil off the page?
No.
Why not?
0.
Okay, so here, note, x equals 0 might be a problem. How do I know if it's going to be a problem or not? Because it's you'll be surprised. How do I analyze this function?
You plug in 0 to the denominator.
You can't. You never do that. It's a blasphemy.
Well, I'm just saying, like, I can kind of eyeball and say, if x...
Eyeball absolute value of 0 over 0? No. You never plug into the denominator, no matter what. You just have a gun to your head. You never do it. I'm going to shoot you if you plug your don't write x in 0 denominator. You're like, nope, not going to do it. What does absolute value of x mean?
Just
Go back to
distance from
algebra.
0.
Huh?
Just distance from 0.
Define it. Give me a definition. What is positive or negative? It's x if your x is greater than or equal to 0. It's minus x if your x is less than 0, right? That's your definition of absolute value, right? So basically this function that I just told you, absolute value of x over x, it's actually kind of like a piecewise function. Now, if my x is greater than or equal to 0, it's going to do one thing, as opposed to if my x is less than 0. So here, if my x is greater than or equal to 0, what does absolute value of x do? Well, it just turns into x, which is 1. If it's less than 0, though, this becomes what? Negative x, which now it's minus 1. So it turns out that if I take the limit as x approaches 0 from the right of this function, what is the answer? It's 1. The limit as x approaches 0 from the left of this function is minus 1. Probably. Now, in a strange way, because of its piecewise nature, it's actually defined at 0. You can notice that f of 0 is actually 1. Because if I'm graphing this function, it seems like I'm going to divide by 0, but I'm not, because it actually breaks into two parts. So it's actually the function 1, but down on the left it's negative 1. So my limits don't match up. I'm defined at the point, but my limits don't match up at the point. So that's a general rule when you have things with absolute values in them. You want to figure out what makes that absolute value 0, and then you have to break it up into two parts. So you have to analyze it in pieces. Example, if you see x minus 3 in absolute values, you're going to think of what does it look like when x is bigger than 3 and when x is less than 3, right? Because x equals 3 makes this 0, which means it's going to take a positive and a negative. It's going to break the function into two parts, right? So in absolute value, something is hidden. You have to be careful with when your function has an absolute value. But one thing I want you to know, another thing I want you to notice with limits, which is an important thing, is that I can analyze a function and I can know how the picture is going to behave before I even draw the picture. Notice that I could have told you this answer. I could have said, oh, by the way, that's the answer. Did I write that down? It's not continuous. Therefore, f of x equals absolute value of x over x is not continuous. Since x equals 0 is in its domain, but it is not continuous. One thing I want to show you, these rules that we have with limits of how to break things up and try to simplify and figure things out, they save us from drawing the picture because in general, functions are really nasty. The functions you'll see in real life, they're not nice. Oh, it's looking x plus 2. Like, the functions tend to be nasty. You're not going to really know what the graph looks like, but knowing when something is continuous, it's actually going to be very important to answer certain questions. So limits allow us to talk about continuity. They allow us to talk about getting close to something. Two things that we will need to do in practice a lot, and we want to be able to do it as easy as possible.
Question.
Yes.
Why is x equals 0 can be in its domain? I thought that the denominator can be 0.
Oh, because this is actually that. X greater than 0, and this if x is less than 0. Right. So there's actually not an x in the denominator.
Okay.
It just looked that way.
Okay.
So other simplifying techniques. Something that we all loved from algebra, rationalizing. Example, limit as x approaches, what did I say, 0. So I gave you that limit to compute. You're not going to want to sketch the graph of this to figure it out, right? It's a nasty function. Even when we do curve sketching, that would be an insanely annoying graph to draw, right? And obviously, I can't just plug in x equals 0. On top of that, it's not clear how to simplify, like how to factor this to be able to cancel that guy in the bottom, right? One thing we do know though, one of these guys have a radical, and there are only 2 terms. So we can think about rationalizing. How do we rationalize?
Conjugate.
Multiply and divide by the conjugate, right? So this is going to be equal to four plus x minus 2 over x. I'm going to multiply that. What's the conjugate here? 4 plus x plus 2, right? You take this guy, you change the sign in the middle. When you do that, you have 2 terms in the square root. What really happens is you kind of have a difference of 2 squares formula here. You have a minus b times a plus b. So we know that that actually simplifies to, what does that simplify to? A minus b times a plus b becomes what? That's right, a squared minus b squared. So that's what the top is going to become. The bottom is going to become this. So the square is going to kill this square root. And this just becomes 4 plus x minus 4 over x times this. Four will kill 4. Then my x I can cancel with this x. So now I just have 1 over the radical of 4 plus x plus 2. And now I can actually plug in x equals 0. Which is 1 over 4 is going to be the answer. So I don't even know what that picture looks like. I'm sure it's crazy. But I know what the y value is approaching when my x value gets close to 0. By the way, tomorrow you're going to see that what that actually is. That's the derivative of radical x when you approach x equals 4. You'll know what that means tomorrow. Which basically means the slope of radical x when you plug in x equals 4 is actually going to be 4. That's kind of it. We have note. writing the limit that thing until you actually take the limit. By that I mean plug in the number. So the easiest limits are the ones where that we can just plug in the number. If I can't just plug in the number, what I try to do is I try to simplify so that I can just plug in the number. Until I get to that point where I actually plug in the number, I keep writing limit, limit, limit. Until okay, now it's okay to plug in that number. And that does it for 2.2. I think that's all I wanted to talk about limits. There's something about infinite limits. We can mention that tomorrow. But yeah, you can actually do .2 homework due tomorrow. Tomorrow we'll do 2.3, which we talk about the derivative. We'll do a lot of techniques. So we'll stop there. But we have homework. So I will take questions on the homework until the end of class. Has anyone seen limits before, or is it your first time?
I've seen limits before.
How many have never seen
Never really worked with them.
Huh?
Never really worked with them, but like I've seen them.
It looks scary at first, but you'll get used to them pretty soon. Don't worry. So, we have a lot of homework, right? It's like 1.5, 1.6, and 2.1. Is that it?
1.3 also.
Oh, we have 1.3 as well?
You don't even know yourself.
Okay, questions on 1.3. Let's start there.
Okay.
Yeah.
Did you push it 39?
39. What does that say?
I don't have to push it right there.
I sort of wrote the question down,
Okay.
if you want to go.
Okay. Surface of ocean, water pressure and air pressure is the same. So surface water pressure increases by that for every 10 feet of descent. Water pressure equals air pressure equals 15 pounds per inch squared at ocean surface. Below surface water pressure increases by 4.34 pounds per inch squared for every 10-foot descent. Okay, so part A says express water pressure as a function of the depth below the ocean surface. I don't know if they gave you the variables, but she has F4 pressure and E4 depth. Let's use that. A. Write F as a function of D. do you do that? Well, it's going to be a straight line. You're changing by an absolute value per unit of descent. So here, I put D, this is the D axis, that's the F axis. So let's say 0 would be when I'm at the surface, that's the depth of 0 below the water. And then this is actually at 15. But then I know for every time I move 10 below the water, I will actually drop by 4.37, right? So if I take 15 minus 4.34, what do I get?
Was it increase? Isn't it increasing?
Increase. Yes, pressure would increase. So the 15 is here, and I'm going to increase by 4 point blah, blah, blah. So I'm here, and I'm going to be here, which is going to be 19.34. Right? Wait, is there something missing here? We have to make sure our units match up. This is inches, and that's feet.
Yeah.
So let's change this to inches. 10 feet is how many inches?
120.
Right, you multiply by 12. So if I'm working in inches here, for every time I move 120 here, I'll have to increase by 4 there. So I just have a straight line that goes through those 2 points, and so I just learned the function. This means my F is equal to, what's the slope? Y2 minus Y1 over X2 minus X1. And what was that? Yeah, well, I kind of wanted the, what's the number? What's this number? Plus
036167.
036167.
Yeah.
So let's just make it 0.04.
Yeah.
That'll be your function. At what depth is the pressure 100? And this is P in inches. You have to keep track of that. Because if they ask you about feet versus inches, you have to know how to change it. At what depth is the pressure 100? That was part E. Call F the pressure. They ask at what depth it is 100 pounds per inch squared. So they ask for inches, so I can just use this formula. So this means I need 100 is equal to 0.04 P plus 15. So this is just going to be 100 minus 15 over 0.04 equals P. So whatever that is, 85 over 0.04 inches below the surface. There's no part C.
I don't
Okay. Any other questions from 1.3?
The answer for A was actually different. It was 0.434 D plus 15.
0.
Oh, for A, for the function, it was, I took it from the back of the book because I didn't know how to do that one, so. It was 0.434 D plus 15.
I think it's because they didn't convert it into 120, they just used the 10. They used the 10 and
Well, I don't, well, it depends on the units, yeah, it depends on how they say the units. I don't have the full question, so it's probably a unit thing. So make sure you read the question and the units match up. Okay, 1.4?
What, 1.5?
1.5? 37? Where does that sit? Does you have to book the whole time? It's a 37?
Yeah.
Okay, so 37, they gave us a graph. It's an exponential function. It says it passes through the point 1, comma 6. And it passes through the point 3, comma 24. They told you that f of x has this form, c times a to the x. And they say find the function whose graph is given. Which means basically find the c and find the a. And that would be the function. So here's my y, here's my x. Basically what this tells me is when x equals 1, my y equals 6. Also it tells me when x equals 3, my y equals 24. So in other words, if my y is equal to c times a to the x, I know two things now. I know that this side is 6 when my x is 1, and I know that this side is 24 when my x is 3. So I have simultaneous equations here. So this is equation 1, equation 2. I want to solve these simultaneously. I can take 2 and divide by 1. So that would mean if I take 24 is equal to CA cubed, I can divide that by 6 equal to CA. 6 into 24 goes 4 times, C cancels C, A goes into this, A squared, which means my A is going to be plus or minus 2, but of course I'm going to take the plus value because this graph is going up. So I know my A is 2. Since A equals 2, I know that in 1, my 6 is equal to C times 2 to the 1, which means my C is going to be 3, which means the graph is 3 times 2 to the x. That would have this graph, and this function will pass through those 2 points. Yeah, so other questions?
Can you do 39?
Yes.
39, show that if f of x equals 5 to the x.
That one was easier than I thought. It was literally like plug it in and then like.
Yeah, you get these two and you. There were tons of ways to solve it, I guess. You could have solved for a and then plugged it in here, or vice versa. But for something like this, I think dividing both sides is, it works. So 39 says if f of x equals 5 to the x, show that f of x plus h minus f of x over h is equal to 5 to the x times 5 to the h minus 1 over h. Okay, so let's actually find what this guy is. F of x plus h minus f of x over h would be equal to, my f is 5 to the x. What is f of x plus h?
5 to the x plus h.
5 to the x plus h in the power minus f of x which is 5 to the x, over h. What's this guy?
It's 5 to the x times 5 to the h.
Right, laws of exponents. Now 5 to the x is common term,
Yeah.
factor it out. What are you left over? 5 to the h minus 1 over h. We're done.
What? That's not real.
What? That's what we were supposed to get to.
It was that easy.
Yeah, that's what I'm saying.
That's what I'm saying. It's all easy. It's an illusion. Things just look scary. Trust me.
Boy, there is one question though about that problem.
What?
The idea of factoring something out for it being a common term implies that that 5x somehow had to have existed in that 5h as well. But it doesn't.
It did. It was always a factor of this.
Oh, so like 2xy, for example. Mm.
41. I could, but I don't think it's relevant for us. That's just a unit conversion thing. So you convert the units, you convert feet and miles into the same units, and then you draw them on the same graph, and then you compare the y values. So it's just getting you used to the graphs and deal with unit conversions at the same time. I'd rather talk about if you have questions on logs.
Okay.
Let's do those now. Yeah, questions from 1.6.
39.
39.
39 is always
Yeah, so like a lot of 39. 39, it says solve the equation. So this is a solving the equation, right? Yeah, we're not giving decimal approximation. We don't do that here. Okay, how do we solve that?
You can divide both sides by 8.
Divide both sides by 8.
Then you can take the log of both.
Right, I want to get rid of this e because I want to get to that x. So I'm going to ln to get rid of an e. And so this will cancel. Here I have 3x is equal to ln of this. And so my x would be ln of 31 over 8 over 3. That's it. Now you can plug that in your calculator and get a decimal, but you'd leave that as your answer if you're in a test or a quiz. And that's fine. Other question?
Mm.
21.
It's similar to the measurement.
Oh,
Yeah, let's do that.
So that's not gonna be on the exam. A question.
No, I'm not going to ask us that.
Okay.
Other questions?
Um,
Anything, like 1.6, go.
19.
Problem 19, start the graph of this, find the graph that was also.
Wait,
Yeah, those were transformations.
Oh.
So are we good with 20? So
21 is literally like, if you have like ln and e, then.
Oh, yeah, which one?
No, not
Okay.
which one is it? How long, how many squares do we go down for, which is a thing that you want to fix?
2.1,
So that's basically
19,
What is number 39?
Yeah.
Can we do number 31 of 1.6? You were confused.
31.
Mhm.
Did you do it? It's healthy.
So 31. Explain why. If I look at ln of x cubed and y equals this and y equals that have the same graph.
But like x squared and 2ln x does not.
But y equals ln of x squared and y equals 2 ln x. Different graph. Okay, why? Can you say why? What do I know about ln? Right, ln is defined for what? What's the domain of the ln?
0 to positive infinity.
Right, 0 to infinity. I can only plug in numbers bigger than 0. However, if I throw an x squared in here, I can now also plug in negative numbers. So this graph will have two wings. So if I look at y equals 2 ln x, it's going to look like ln x but stretched vertically to 2. However, if I look at y equals ln of x squared, it's going to look like this, but now I can also plug in numbers over there. Right? So there's a whole other wing now because my x's can take on negative values when before it couldn't. Here it can. Right, so algebraically these are the same things, but graphically they're only the same on one side. However, of course with x cubed, I can't plug in negatives here or here. Right? So they both will have only the right side and they'll look exactly the same. Right? These are exactly the same for positive x's, but this one allows me to plug in negative x's as well. That's basically it. So I have a left side to that graph. Okay, 2.1. Projectile motion. Okay, so they gave us a function here. The height in feet of a baseball t seconds after being thrown straight up is given by this function. Find the average speed. For t goes from between 0 and 1. T is between 0.9 and 1. Technically that's 3. T is between 0.5 and 1. T is between 0.99 and 1. B. Estimate speed after 1 second. Okay. We'll need Probably need some calculators here to get the full idea of what's going on. But yeah, it's talking about average speed, which is average rate of change is what we're going to look for, right? So basically for 1, I'm going to look at h of 1 minus h of 0 over 1 minus 0. Basically what I'm doing. So h of 1 is going to be 36 minus 16 minus h of 0, which is 0, over 1. So I take 36 minus 16, I get what? 20. So the average speed is 20, what were the units here?
Feet over a second.
Feet per second. 20 feet per second. That's how, on average, how fast it was moving. 2, here I'm going to need h of 1 minus h of 0.5 over 1 minus 0.5. So that's again going to be 36 minus 16 minus, in brackets, 36 times 0.5 minus 16 times 0.5 squared over 0.5. What's that one?
It's 12.
12?
The answer is 12.
Okay. Yeah, because this is like a half, that would be a quarter. And yeah, things should cancel out nicely here. 3, here I'm going to find the average rate of change between 0.9 and 1. So it's h of 1 minus h of 0.9 over 1 minus 0.9. 36 minus 16 minus 36 times 0.9 minus 16 times 0.9 squared over 0.1. What's that?
5.6.
5.6. 4. Here, let's take h of 1 minus h of 0.99 over 1 minus 0.99. So this is 36 minus 16 minus 36. This is minus 16 is 20 minus 36 times 0.99 minus 16 times 0.99 squared in brackets over 0.01.
Four.
It's 4, exactly 4.
Yeah.
Okay. So then B, it says estimate the speed of the after 1 second. What would your estimate be?
4.
Speed after 1 second is going to be pretty close to this one, right? Because here the time window between of 1 second is really small. So you're gonna, you see that it's slowing down. It started at 20, then 12, then 5.6, then here. So you expect this to be roughly here. So it's going to be roughly 4.16 feet per second. It started out moving fast, but then as it started reaching 1 second, it was slowing down. Other questions? We can end there. Try the limits questions. We'll do that.
Okay, where do I leave?
Drop the homeworks here.
All just like that?
It's not deliberately messy. Remember file. I'm thinking of giving a quiz on Thursday again. You guys on your toes. It's gonna be everything since the last.